Oualid. I'm a researcher at the Algerian Space Agency, more specifically the Centre de Technique Spatiale in Erbil. And today I'm going to present to you the research that I've been doing for the past 2 years. The presentation plan will go as follows. We're going to kick off this presentation by a small introduction, like the motivations and the objectives behind this research. We're going to explain why existing technologies will not work in our case, and why methods that use a single sensor will not suffice as well. All of them have limitations. And we're going to explain why data fusion techniques can be the solution to those limitations. And we're going to explore the design soil moisture content estimation pipeline, as well as the study areas that were used to validate it. And finally, we're going to analyze the results achieved in this research. According to the United Nations report, more than 70% of freshwater withdrawals are dedicated for agriculture alone. And more than 80% of that 70% is for irrigation purposes only. And you'll be sad to know that most farmers actually over-irrigate their crops. They use 2 to 3 times the recommended amounts for their crops. And this doesn't bode well for Algeria, as you can see by this map. This map is a forecast of water pressure in the future, I think in 2040. And Algeria will be using more than 80% of its fresh water withdrawal. So we need to minimize our water consumption, at least for irrigation purposes. And one way to do that is by knowing actually how much water actually is in those agricultural fields. And in order to do that, we need to actually observe a very important factor in the hydrological cycle, which is soil moisture. Now, soil moisture content can be defined as the amount of water present within unsaturated water particles, soil particles, sorry. And it can be found in 2 zones, surface zone and the root zone. Obviously, we are interested in the surface zone, since we're doing remote sensing here, and we can't really sense root zone soil moisture. Soil moisture can be important for many fields. Mainly irrigation scheduling, agricultural drought assessment, climate change, and so on. The main objective behind this research is to design a system that is capable of effective and precise estimation of soil moisture, at least 1 sensor, and is to achieve better accuracy through data fusion techniques by fusing these estimations through multiple levels of data fusion, feature level fusion and decision level fusion. The first question you'd ask yourself, why bother? Why not just use an existing technology, mission purpose satellites? And you'll be within your right to ask that question, because those satellites are actually quite good. They have very, very low retrieval errors. At worst, it can be 77%. And then they have a high temporal resolution. They have low revisit time. It can sometimes be twice a day. But the issue is the spatial resolution. So it's in the order of, well, in best case scenario, 3 kilometers. And since most farmers, family farms, which are less than 2 hectares, represent more than 70% of all agricultural land, this is quite a problem. So we need high spatial resolution satellites to do that, and the most abundant ones are the multispectral ones. So we used this method, which is called the perpendicular drought index. It's basically used as a juxtaposition of, in terms of reflectance in the presence of water, in the red and the near infrared bands. And through this equation, we can actually estimate an index that has a linear relationship with soil moisture content and high correlation with soil moisture content. Its issue is that it has this soil line, and the soil line can be quite subjective from one data set to the other. Therefore, we needed to seek other means, other methods. So we tried a simple algebraic combination of the bands, especially bands sensitive to soil moisture, water presence, and the normalized difference water index and the modified normalized difference water index are great candidates for that. Obviously, before we go to the next method, these methods are multispectral. They have limited abilities in terms of representing the soil moisture properly, especially in the presence of vegetation cover. So we needed to try another method that is resistant to vegetation cover presence, which is the popular LSTVI feature space. LST stands for land surface temperature, and VI stands for vegetation index. Now, vegetation index is a great way to represent fractional vegetation cover. And if we plot a VI as a function of, if we plot a surface temperature as a function of any vegetation index, we will receive, we will get this triangular shape, with the hypotenuse of this triangle representing the dry edge, which means any pixels close to this edge have very low soil moisture content values, and any pixels close to the wet edge actually has high soil moisture content values. Now, as you can see, this suffers from the same limitation as the PDI, which is basically these extremities are subjective from one data set to the other. However, they have a linear relationship also with soil moisture content, and they have high correlation with soil moisture as well. Now, this may have another issue, which is unless we have pixels, well, the distribution of pixels in terms of vegetation cover are, well, more or less close, it will skew from one area to the other, which means if you have full vegetation cover, that data set will not be used in other data sets. And obviously, the methods that I presented up till now are all passive sensors, so they use the sun energy to estimate stuff. But those kind of sensors have a problem in terms of cloud coverage and nighttime. So basically, we needed other type of sensors, which is active microwave sensors, or more specifically SAR. And one of the most popular soil moisture content estimation methods through SAR is the integral equation model. And it uses the implicit relationship of the dielectric constant with the soil moisture content. Well, that's what we're using to estimate soil moisture content. However, it has a very, well, let's just say, limited validity range. We're speaking about the surface roughness profile of the fields that we're inspecting. So we took a couple of measures to correct that, and that's by adding a new calibration, semi-calibration parameter developed, and we used a different kind of integral equation model. It's called the empirically adopted empirical equation model, and this one has a higher validity range. Now, while SAR is very reliable, very effective at estimating soil moisture content, it has so many constraints that can affect its performance, mainly bands, basically, if we are frequency. So if we're estimating soil moisture using a SAR that has the S band or the L band, we'll receive better results than ones we receive with the C band, mainly because they offer more penetration and they are more resistant to vegetation cover. So as you can see, each of these methods have its own limitations. So it's a very good case for us to use data fusion techniques to try to remedy that. Before we go through that, we need to stress that the inversion of the EAIM is mathematically very complex. So in literature, what they do is use artificial neural network to do that instead. So in terms of data fusion, the first level we've done in data fusion is the feature level fusion. So basically, we extract features that are relevant to soil moisture content, and we concatenate them together in joint feature vectors. And those joint feature vectors are fed to this artificial neural networks, or in our case, 10 artificial neural networks. And this has been a success in past studies. So inspired by that, we wanted to take this a step further and see if decision level fusion would actually fare any better. Now, we've done that through the fully constrained least square and the Bayesian inference. We use these methods to assign 10 weights to each of the estimations that I just presented to you. And we achieved very good results doing that. Now, before going to the SMC estimation pipeline, we need to stress that we used we used Landsat 8 and Sentinel-1 data for this work. Now, this is the system we use to estimate soil moisture. Basically, the pre-processing is done separately. Each of the sensors are pre-processed separately. Then all of the images are resampled and co-registered, and all of the relevant features are calculated, then fed to 10 artificial neural networks. The estimation of all of these artificial neural networks are fed to the fusion center, where weight will be assigned for each of the estimations. Then we used the Bayesian inference and the FCLS to calculate those weights. In the end, we'll have this final SMC estimation, and we'll store these weights for future executions. We needed study areas to validate this work. So I had to collect soil moisture content data from two study areas. One in the UK, more specifically in the southwest of the UK, in a place called the Blackwall Farms. It's a relatively small field, and it has a clay loam, which is famed for its water retention capabilities. At the time, it has minimal vegetation cover, and it was recently plowed, so surface roughness had been quite high. The second study area is local. It's in Sidi Rashid in Tipaza. Obviously, the soil type was not as good, and its water retention capabilities are quite low. However, this study area is a bit bigger than the one in the UK, and it had, let's just say medium vegetation cover. Now, on to the results. So as you can see, right from the beginning, the feature level fusions actually outperform any method that uses a single sensor, but the decision levels fusions, especially the Bayesian inference, actually achieve the best results. When I say the best results, it's less by almost 1% than any of these methods in the Blackwall Farms, and less by more than 2% in Algeria. For a more in-depth view, so basically, the end game, we want the end user, which is the farmer, to use something that is relatively easy to use. It can be used as an API or an Android application. Well, that's down in the future. But what we want is geocoded soil moisture content map. And as you can see, the ones that are estimated here are very close to the one that is actually measured. It is reflected in terms of correlation and low root mean square error In the case of Bayesian inference, it's almost, well, it is less than 1%. And if we inspect the mean, the max, the mean, and the standard deviation, they're quite close or identical if we're speaking about the mean. So the second study area was had higher standard deviation, which means it had more generality if we're speaking in artificial neural network terms. And as you can see, any farmer could just use, well, red means bad, green means good. So basically they're just water these areas instead of watering the whole field. And that would minimize their water consumption, basically. Again, the mean, the max, and standard deviation are quite close. Although in the case of the FCLS, the standard deviation is a bit lower than the measured one. Well, to conclude, the proposed system actually produces lower root mean square error, and that's the objective that we set to ourselves, which is quite good. In the case of Blackwell farms, the results are, well, the root mean square error is lowered by almost 1%, and in the CD Rashid by more than 2%. The Bayesian inference method produced the best, well, the most accurate SMC estimation in all of them. The system performs its best in the absence of intense vegetation cover, so more investigation will be needed to understand why. The system also struggles estimating SMC values when they are less than 20%, also subject of more research. This system produces good results, but it still has room for improvement. Mainly, the subjectivity of the dry, wet, and the soil lines needs to be addressed, and that could be done through the future consideration of parabolic and theoretical boundaries instead. The risk of overfitting is also an issue, so we need to add more data points, and we can do that through a collaboration with the Cosmic Ray Soil Moisture Monitoring Network. And the number of surface roughness parameters are essentially quite low, so we need to work on that as well. And the temporal gap. So basically, because we're using data fusion techniques, the acquisitions of Landsat 8 and Sentinel-1 are not the same. So there is a gap of 2 to 3 hours at least. So in order to bridge that gap, we need to using additional satellites such as Sentinel-2, or after the successful launch of Landsat 9, or ours. So references, and thank you for your attention.
Few minutes for questions, if you have any. I think here we have doctorate students working on computer science and biology, so you are welcome to ask your questions to Dr. Yahya. Any question?
Assalamu alaikum.
Salam.
So thank you very much for your presentation.
Thank you.
It was very clear. I am not a biologist, or so I cannot go through your mathematical formula, but I have just a general question. So I am wondering how could we take profit from this moisture content estimation techniques, especially in Algeria?
Well, basically, I spoke to actual traditional farmers in Biskra, where I'm from, and they have issue of high water bills. That's because they irrigate uniformly, so they just let the water go, and when they think it's enough, it's enough. But if we use these maps, we're just going to use, as I showed you earlier, the red pixels. So we just irrigate in those areas instead of irrigating uniformly. And when we do that, we minimize minimize water consumption. Yeah.
Thank you.
Thank you.
Other question?
Non,
Oui, même en français, vous
يمكن
pouvez poser, bien sûr. vos
تقدروا
questions.
تهضروا بالعربية بالفرنسي كيما حبيتوا.
La langue, c'est un
La-
outil, Barka. Donc,
إيه.
c'est un outil. On comprend les trois langues. Heureusement pour nous, donc on a cette opportunité. Donc on maîtrise l'arabe, le français, l'anglais. Donc, oui.
Merci pour votre présentation. Juste une petite question.
Oui.
Alors, imaginons un contexte opérationnel de votre solution.
Ok.
Quelle est la fréquence de mise à jour des cartes d'humidité?
Mhm.
Et est-ce que vous pensez que ça correspond aux besoins sur le terrain, etc. Parce que les satellites, il y a des temps de revisite, il y a des... c'est-à-dire on a une certaine granularité qu'on ne peut pas dépasser. Et donc, comment vous voyez les choses dans un contexte pratique?
Okay.
Merci.
Excellent question. أنا ريبوندي بالفرنسي عربي. Okay. Okay. Very good question. So basically, the reason, if you've seen in the objectives, we're using a reconfigurable system, which means it can still work even if we're losing one satellite. So we can just use Landsat 8. So the system is made reconfigurable enough that if it loses one component, it's still going to work. So down the line, there will be constellation for all satellites. For instance, next example is Sentinel-1 and Sentinel-2, and recently Landsat 9. So in the future, there will be high revisit time. In terms of soil moisture content, well, it depends on the soil itself, because in the UK, it took days without changing. But in Algeria, it takes hours. So it all depends on the scenario, but it's very feasible. So if the data is available, if we've done enough training to avoid overfitting, I think it's very feasible.
Merci beaucoup. Donc, il y a d'autres questions?
Well, thanks for your presentation.
No problem.
Please, just I have one question.
Oui.
What's the limitation of your solution?
Mhm.
And when we use underground things and environmental data sensors, which the best solution?
So environmental, satellites that are used in environmental studies actually use lower spatial resolution because they want to look at the things globally. Instead, we're working on something that is very small, like in less than 2 hectares. So we need to work with things that hopefully less than 100 meters. So if we're using that, we're going to use multiple satellites. The glaring issue would be temporal gap between the satellites that we're using. So the data, the ground truth data, will be more correlated to one satellite more than the other. Now there are some things that we did, like taking the measurements between the acquisitions, so the ground truth would be equally correlated to both satellites, but it's still an issue. The other issue is the ground truth measurements. So there is no network at this time that can present us with high resolution ground truth. So you need to go to the field and take them by yourself. So in my case, just 110 took me more than, well, at least 2 hours, more than 2 hours. So that's without the pre-processing, the geocoding of those measurements. And yeah, so it's a lot of work. So hopefully, like if we can like rescale this effort of getting these ground truth measurements using teams instead of one person, like a lot more ground truth. If we get a lot more ground truth, it means more accuracy.
But for me, the soil moisture parameter is not enough to calculate the quantity of water for irrigation. So
well, it's one parameter. It's not all parameters, but it's one important parameter. Yeah.
So you calculate the quantity of water take into consideration the soil moisture parameter just.
Yeah, just the soil moisture parameter. There is the SWOT model, if you're aware of it, and you can use that to try to get an idea how much water actually is there. But in the end, it's going to be just an estimation. So it's just a simulation of a model that we don't know the truth of. But when we are estimating soil moisture content, we have like a marginal shadow of a doubt in the root mean square error, but we are actually measuring something. So we can use that parameter to actually know how much water actually there. Obviously, this is not the last step. This is just one step to open up the conversation, you know. And I'm more than happy to have other people that are more agricultural oriented to, you know, enrich this work. Yeah.
Thanks.
No problem.
Par rapport à la question qui a été posée par le est-ce que l'estimation de la teneur d'eau dans un sol et à quelle profondeur suffit pour pouvoir arriver à déterminer la dose d'irrigation?
جوستومون دوك هو بوز لا كيستيون هذا قلت له انا بدي ورا بارامتر واحد من لي بارامتر مش كومبلي تسمى تقدر تقبض هذا البارامتر كاين دي موديل تنجم تسيميلي بهم قداه كاين المالتم وهذاك قداه تحتاج الماء تو ديبون على ليسبيس تاع البلان تاعك تيب تاع الاخر تاع السويل لار اوف ثينكس بصح كيما قلت له انا هذه راهي بريميير ايتاب تسمى تعود عندك لانفورماسيون هذه مع الموديل هذه مع الكونيسونس تاع الشون اغريكول تاعك تنجم دير به حاجه تنجم تميني بزيد به صح.
Bon, merci docteur Oualid pour cet exposé oral, cette présentation. Donc malgré que je comprends l'anglais mais je ne sais pas comment m'exprimer, il y a des coupures. Voilà, pour qu'en est-il, parce que vous avez travaillé sur des sols donc, à l'air libre, donc découvert, et qu'en est-il pour les serres de culture? Est-ce que donc, vous faites les mêmes, vous arrivez à donc, concrétiser ça avec des formules, les mêmes formules, ou bien il y a d'autres formules pour estimer cette humidité au sol? Parce que maintenant, il y a beaucoup de cultures de serre. Donc, est-ce qu'on peut, c'est la même chose pour calculer, ou bien il y a d'autres conditions qui vont interférer, donc en comparant les deux types de culture, soit à l'air libre ou bien au niveau des serres.
اوكي دوكا احنا واش رانا نديرو لهنا رانا ناخذوا ايرث اوبزرفيشن داتا تاع الساتيليت هذو نحاولوا نقيسوا فينومين فيزيك الفينومين فيزيك هذه في الكيسيون تاعنا هي سويل مويستر دوكا جو سوي كونسيون بلي كاينين دوطر فاكتور اللي لازم يتكالكيلاو مي بور لو مومون انا راني في الفولي هذا تاع سويل مويستر حد نعرف بلي كاين سويل مويستر نو دوكا كاين بوسيبيليتي تاع كاينين بريزونس تاع محصول ولا كش حاجه مختلفه من اي حاجه لحاجه هذا السيستم مش عادي بيرفورمي كيما تعود كيما فوالا الور لازم لنا دي تيست سبليمونتير باه نعرفوا شايف تسمى لازم لنا نزيدوا نروحوا ونبدلوا لي سبيس نبدلوا الاخر كذا كيما كنت نحكي له راني نروح فيزيكمون ونهز هذو لي ميزيرمون تسمى عادي يعود النومبر ليميتي فوالا وميم كابتور هذاك ما عادش عندي دوكا بور لو مومون شايف تسمى لي دوني اللي عندي نحاول ندير بهم لو ماكسيموم مزيان
Donc, voilà, donc une petite attestation.